Welcome to this video tutorial about feature transformation. We're going to start with the iris dataset. As we already saw in previous videos, this is a dataset which has several features which are highly correlated. We have a lot of high correlations in the correlation matrix. This dataset has 150 instances and 4 attributes. We couldn't have to reduce the number of dimensions. The rule of thumb that I taught you in the theoretical part of the course, that the number of dimensions raised to the square should be much less, about 10 times less than the number of instances is fulfilled. This is 4 square is 16, multiplied by 10 is 160, 150 is fine, it's within range. I will feel perfectly fine going ahead. But despite that, given that this is a dataset that we understand in detail, is going to be the first one with which we're going to use the principal component operator. The principal component operator, as any operator within RapidMiner, has an input port for the data and has an output port. This output port will provide the transform data. If I want to see the original transformation, the original data, the original, that's the meaning of this port, original. Over there, I will have the original and modified dataset. Some operators in RapidMiner have that port when they change the data, because this operator in this port is going to provide the PCA transformation. The pre is the result of the transformation, the rotation matrix pretty much. By default, PCA keeps 95% of the variance. That's the default threshold that it uses. If I run the process, this is the new dataset. It has 2 components, so I just need 2 components to actually capture 95% of the variance of the original data. These are the components. PCA is 0.362 multiplied by the first attribute minus 0.082 multiplied by the second one, and so on. This is the linear transformation that yields PC1, PC2, PC3, and PC4. Remember, in PCA, we move from an n-dimensional feature space to another n-dimensional feature space. And then we use some threshold to remove some of these dimensions, but initially we have 4 dimensions. And the threshold is based on the variance, on the cumulative variance typically. Over here, for example, this graph over here is showing that the first component is capturing 90-something% of the variance. As a matter of fact, if I go back here to the eigenvalues, I have over here that information is capturing 92.25% of the variance. The next one, it's already over 95%. That value is probably close to 98%. Again, if I go to the first table, the second component, PC2, is capturing 0.05 additional variance of 5% and is moving the cumulative, the overall variance of the first and the second component to almost 98, slightly under 98. With the third one, we already are at 99, and with the fourth one, of course, we also have 4 dimensions, is 100%. If I change the threshold and, for example, say that I want to capture 99% of the variance, I run the process again, and in this case, I have 3 components, because to reach, and this is exactly the same data as before, is the same transformation, to reach 99%, I have to go up to here and not just up to there. However, if I said that I just want to have 90% of the variance, which more or less is around here, one component is, around here, below the first dot over there, a single component is going to be enough to capture 90% of the variance. So if I'm fine with keeping 90% of the variance, one component will be enough. As we explained in the theoretical part of the course, variance is used as a proxy for information. The more variance we capture, the more information we have. You may also check, if you want, how the different components, let's go back to 99%, 3 components, the different components that PCA generates are completely uncorrelated. They are orthonormal to each other. If you compute the correlation matrix of the components, the correlation between them is 0. Let's change the dataset and let's load a more realistic dataset, which will indeed need PCA, or that I at least prefer to analyze applying first PCA. I'm going to use the read ARFF format, the WCA format, and I'm going to load the Wisconsin Diagnostic Breast Cancer Database. We already loaded it in another video. It's within classification, Wisconsin Diagnostic Breast Cancer Database. Let's check also the original data. And I'm going to let the operator with the default value, which is a fine value, 95% of the variance. So we allow up to 5% of the variance to be discarded. Okay, fails because this dataset has one column for the class. But given the way we load it, AI Studio doesn't know that that column is the class. I need to use the set role operator to specify that the operator whose name is the attribute whose name is class is the label. Given that is the label, now is going to be ignored when computing the PCA transformation. Let's start by visualizing the correlation matrix. We have many high correlations. This is a highly correlated data set. And if we plot a few of the data, this is the original data set. I'm going to generate a scatter plot matrix with a few of the features. We see that there are some very highly correlated features. It's also true that this correlation over here is non-linear. There is a light curve. This one is linear. There are other features such as that one or that one over there, which are also linearly correlated, but not that strongly. And there are some features such as that one over there where correlation is very low or nil. So there is a little bit of everything, although mostly high values, some low values, 0.0 something, so 0.2, that's not very high either. So there are some low values and many high values. This is a highly correlated data set. And that's good news because in this case, we have 30 attributes and 569 examples instances. 30 squared 900, multiplied by 10, 9,000. I'm very far from 9,000 data points. So the PCA transformation makes sense here. I apply the PCA transformation, keeping 95% of the variance. And it seems that the first component already captured 98.2% of the variance. Look at this graph. The first component is already capturing 98.2% of the variance, and the remaining ones, the second one about 2%, and the remaining ones pretty much nothing. So given that I asked for 95% of the variance, only one component has been output. The result is absolutely ridiculous. It makes absolutely no sense. This cannot be the case. In reality, I have some features which have very small correlations. If all the scatter plots look like this, okay, I may believe this result. I may believe that I can go from 30 to one dimension, losing just about 5% of the data. But something has gone really wrong because there is pretty much no correlation over there and not that much correlation over here and pretty much no correlation there and there. And despite that, PCA believes that a single component is fine. Let's check the rotation matrix over here. Let's check the first component. I'm going to sort the values which multiply each of the original features for the first component from highest to lowest. We see that the first component is 0.85 multiplied by A24 plus 0.5 multiplied by A4, and then there is a few more components which have a tiny contribution, 0.0 something, and the remaining components have no contribution. The first component is pretty much A4 and A24 and a little bit of a few more components and nothing else. These two components are mostly what is involved in the first principal component, which seems to be capturing 98% more or less, 98.2% of the variance. What's going on here? Let's check those two components. Let's check some statistic information about that. And for example, these components go from 100 to 4,000. That one over there from 50 to 200, and this one from 0.001 to 0.03. Check the range of that component and the range of this one. This is the component with the highest maximum value and the highest range. We are having the issue that I explained in the theoretical part of the course of comparing houses with euros. For Euclides, one house equal 1 euro. 1 unit in all the dimensions of the feature space has the same impact, has the same variance. In practice, one house is worth many hundreds of thousands of euros. Typically, it's worth a lot of wealth. But the machine learning algorithms don't know that I may have a lot of variance here and very few variance in A20, but maybe this attribute is very important. If we check A4, we see the same. It goes to up to 2500. It goes to up to a very large number, much larger than the other components. This showcases how it's important to normalize the data before applying PCA. If not, the variance is not going to be comparable. In the IRIS dataset, we could also have done this and we will have got slightly different results, but in that dataset is fine, more or less. It's fine, more or less, because all the 4 features we have are in the same units. They are a few centimeters. They are the length and the width of the petals of the sepals, so they are comparable. We don't have very wide different ranges, such as in this case. Over here, the normalized operator has different normalizations. We're going to be normalizing all, and we have different options. For example, range transformation, which goes from 0 to 1 by default, but we may change it. This is one of the normalizations we covered in theory. And the one that AI Studio calls zeta transform is standardization. It converts the data to a new feature with mean 0 and standard deviation of 1. If I run the process again, now I got back 10 dimensions. So we move from 30 to 10. This could be believable because after all, in this data set, I do have a lot of highly correlated features. So this could be feasible. Indeed, now, if we check the PCA, now the first component has contributions of many more features. Some of them they contribute less, some of them they contribute more, but this makes more sense. And the first component is capturing 44% of the variance, not 98 like before. By the way, these values, the contributions of each of the features to the first component, these numbers, this column over here, could be considered as a feature selection technique. This is giving us a measure of how relevant each of the features are. The first component is capturing the most variation of the dataset. The A8 component is the one which has the most. It will be the most useful feature, and the A15 is the one which has the least. It will be the least useful feature. AI Studio has a filter attribute selection method, which is called PCA, and is based in this, in which I just described. It computes the PCA transformation and uses the loadings of the first principal component to estimate how useful each of the different dimensions are. Okay, let's work with another component which could be useful for this dataset. I'm going to forget for a moment about the PCA transformation, and I'm going to output over here the original data, or well, better just not to converse on this. I'm just going to remove it. And I'm going to show the shape of the A24 attribute, which was the one which had the highest range. This is an example of a long tail. Most of my data is here, but I have a few of very large pieces of data and a few over here. As we explained in theory, when we have this type of distributions, it's very often the case that it may be a very different situation to be in this bin than to be in this other bin. But typically being in this bin or in the one below or in the one after, it doesn't make a lot of sense. It's very different situation to have 100 euros in the bank or 10,000 euros in the bank, but having 1 million 1,000 euros or 1 million 10,000 is pretty much the same. This attribute could be a candidate to apply a nonlinear compression. There is an operator which is called generate attributes within RapidMiner. And this generate attribute operator allows to implement, I'm going to call it logarithm of A24, allows you to, logarithm A24 allows to implement pretty much any mathematical operation over one or several attributes. Over here, you can create your formula. If you don't know the syntax, you can look for the different functions. Over here, for example, we have different mathematical functions. One is the logarithm, and over here, I'm going to type the name of the attribute, A24. You could keep adding, for example, plus A15 and divided by A11. You could write, you could write any mathematical formula here using if you need different mathematical functions. Right now, the only one thing we want to do is to apply a nonlinear compression to the attribute 24. Is the logarithmic compression. I may have used the square root or the cubic root, but I'm going to use the natural logarithm, and I'm going to call the feature logarithm of A24. And if I run the process, okay, there is some issue with the formula, probably. Yes, I have an extra parenthesis over there for some reason. Logarithm of A24. Now I have the new attribute. And you see that this attribute doesn't have such a large tail first, and it looks like there is a normal distribution here and maybe another normal distribution over there. This could be a binormal distribution corresponding to the two type of instances. Let's color by the class. And let's see what's behind the green color. Indeed, I'm not very far from having two Gaussian-like distributions. especially the first one, for the two classes, the Malin tumors and the Benin tumors. Compare this with the histogram for feature 24. Here the tail is much longer. This is much farther from normality. This is not normal either. Over here there is a lot of data and there is probably even more overlap. So this shows the utility of a nonlinear compression to get rid of a long tail in a distribution. Let's go back to the iris dataset and let's apply other transformation, which is discretization, which in RapidMiner is called binning. If you select discretize by binning, you choose the number of bins, for example 4, and if you run it now, the iris dataset is made of 4 nominal attributes, each of them with 4 possible values, which are labels: small, medium, large, very large, for example. This strategy, the one we have used, the discretize by binning, it uses the equal with bin. That's why this distribution is so uneven, and this one is also quite uneven. What it has done is compute the maximum and the minimum of each attribute divided by 4, and that's the width of the bin. If instead discretize by binning, we use discretize by frequency, it will try to keep a constant density of instances in each of the bins, and in this case, the distributions will be much more even. Not perfectly even, because there may be no way of getting perfect density, because there may be for some end of the bin, these 3 instances enter in the bin. If I decrease it for 1 unit, those 3 instances go to the other bin. So it's not perfect, but there are much more even distributions. There is also an option to discretize based on user-specified parameters. For example, if you're discretizing age, and there are some ranges of age which have some physiological value, some physiological meaning, you can specify it by hand those ranges. Another operation, and I'm going to drag the Gulf weather dataset, however you want to call it, is the opposite, is moving from something which is a label, and this dataset has a label for outlook and a label for wind, to something which is a number. There is an operator called nominal to numerical. There is other operators, nominal to binomial, may be applied if the thing we load was loaded initially like a number, but in reality is binary, 0, 1. Numerical to polynomial is when RapidMiner believes something is a number, but we want to turn it into a label. So there's different operators and in blending attributes types, which help us change the type of attribute. There are also operators to work with dates in the case that you have dates in your dataset. But the one I wanted to use now was nominal to numerical. I want to turn something which was a label into something which is a number. If I run the process, now I got 3 variables for outlook. The possible values were raining, overcast, and sunny. So I have 3 binary variables for outlook. I have 2 binary variables for wind, true or false. If instead using the dummy encoding, I use unique integers, which could not be a good idea, honestly, for outlook, because I'm not really sure which outlook is twice larger than this other outlook. In the case of wind, may be fine, because either there is wind or not. So for wind could have been a good strategy, but for outlook, in this case, honestly, I would not feel comfortable. I would prefer the dummy encoding. I could have used the select attributes operator, or I can indicate here that, for example, I want to apply this to a single attribute, and the attribute is wind. And now I will be turning into a number just wind, and I feel comfortable having a binomial label, a number for wind, But for Outlook, I do believe that we should use the dummy encoding because there is no order relationship. It will apply it over the only remaining non-metric attribute in this dataset. And now we have here the three dummy variables to code for Outlook and the binomial variable to code for Wing. And we have a completely metric weather dataset. It's important to remember that there are some techniques which can only handle a certain type of data. A decision tree or a rule-based system can only work with nominal data. If you have numbers and if you train a decision tree, at some point somehow those numbers were turned into labels. Or a neural networks or a support vector machine or a regression can only work with numbers. If you had labels, you have gender in the dataset, somehow at some point was turned into a number. Sometimes what the tool is doing by default, it may be fine, but in other times it can be interesting to expect, okay, how exactly did my decision tree turn the age of the patient into a label? And is there any other way of discretizing the age, which was originally metric, into labels which are, for example, more meaningful from the point of view of the doctors, from a physiological point of view? So keep that in mind. Sometimes some operators within AI Studio, they work even you are feeding mixed data to some model, for example, a decision tree that can only work with nominal data, or a neural network that can only work with metric data, with numeric data. But they work because there was some automatic transformation, and maybe that transformation was not the best one for your problem. That's why it makes sense sometimes to manually change the type of some of the operators. The last operator I'll mention briefly is just the sample operator. You can either specify an absolute sample size, so we're going to select 100 instances from the iris dataset, 100 instead 150. We could select a relative sample size, for example, let's keep 45% of the data. So we're going to select 45% of the instances. Okay, sorry. Okay, it revived. So we have 67 examples. And there is another operator which is called sample bootstrapping, which samples with replacement, where I may ask for a sample for a relative sample of 200% too. And I'm going to get back 300 instances, which of course were sampled with replacements, or there'll be multiple instances which were just copied. Split data may be useful, and we already have used it at some point during the course to split the data. Over here, we will be splitting in proportions. For example, I may specify that I want the first output port to have 80% of the samples and the second one 20%, right? So this will be the connection I'm doing now will contain 20% of the data and the other 80%. And that's everything for this data transformation tutorial. See you in the next video.